Hey there, and welcome. Today, we are diving into the hidden rules that run, well, everything. I'm talking about the steam from your morning coffee all the way to the expansion of the entire cosmos. So, yeah, grab a cup of something warm and let's get into it. I know, it sounds a little out there, right? But seriously, that simple cup of coffee is the perfect little laboratory for understanding some of the biggest ideas out there. It's all about the flow of energy and the nature of change. It's kind of the gateway to the whole thing. Ready? Let's go. Okay, so first things first, before we can get into any of the big rules, we have to know what we're actually looking at. In thermodynamics, we basically split the universe in two. There's the system, that's the thing we're interested in, and then there's the surroundings, which is literally everything else. So if our system is the hot coffee in your mug, the surroundings are the mug, the air, the table. You get the idea. Now, this is where it gets really practical. Your coffee cup is what we call an open system. It lets out heat. That's energy, and it lets out steam. That's matter. But what if you put a tight lid on it, like a sealed water bottle? Well, heat can still get out, but the water's trapped. That's a closed system. And the holy grail? The perfect thermos. It tries to stop both heat and matter from escaping. We call that an isolated system. It all comes down to what can cross the boundary. Great, so we've defined our little corner of the universe. But things don't just sit still, do they? They change. Heat moves, gases expand, stuff cools down. And these changes, they aren't random at all. They follow really specific paths or processes. Let's look at the 4 big ways a system can change. So here they are. These 4 are the absolute building blocks. You see them everywhere, from the engine in your car to what's happening in stars billions of light years away. They all describe a change where one important thing is held constant. Let's break them down real quick. First up, isothermal. Iso means same. Thermal means heat. Pretty straightforward, right? This is any process where the temperature doesn't change. Think about letting the air out of a tire, but you do it so slowly that the tire just stays at room temperature the whole time. That's isothermal. Next, we have isobaric. Baric is all about pressure. Think barometer. So here, the pressure stays constant. You see this one every single day. When you boil water in an open pot, the steam expands, but the pressure is just the constant atmospheric pressure in your kitchen. That's a perfect isobaric process. Then there's isenchoric. This is where the volume is locked in place. It can't change. The best example is a pressure cooker. The pot has a fixed volume, right? But as you crank up the heat, the pressure and temperature inside go through the roof. This is an isochoric process. And hang on to this one, because it's actually super important, as we'll see in a minute. And finally, adiabatic. This is a change that happens either in a perfectly insulated system, or it just happens so blindingly fast that heat has no time to get in or out. Think about what happens inside a car's engine cylinder. That compression of fuel and air happens in a fraction of a second. It's too quick for heat to escape. That is a classic adiabatic process. Okay, so we have our systems, we have the different ways they can change. So what's the big rule that governs all of it? Well, that brings us to one of the most important, most fundamental principles in all of science, the first law of thermodynamics. And there it is, just 3 words, but wow, this is the big one. You cannot create energy, and you cannot destroy it, period. All you can do is move it around or change what form it's in. This isn't a guideline. It's a fundamental, unbreakable law of the universe. So this is the mouth that makes it all work. The best way to think about it is like an energy bank account. The change in your account balance, that's delta U, the system's internal energy, is just what you deposit minus what you withdraw. The deposits are Q, the heat you add to the system. And the withdrawals, that's W, the work the system does on its surroundings, like a gas expanding. It's a perfect accounting system for energy. Now, remember I said to keep an eye on that isochoric process, the pressure cooker one? Here's the payoff. If the volume can't change, the system can't expand or do any work. So in our little energy equation, W, the withdrawal, is 0. The formula just becomes delta U equals Q. Every single bit of heat you pump in goes directly into jacking up the internal energy. That's a massive shortcut and a super important tip to remember. Okay, so far we've been talking about these really clean, defined processes. But there's one last really crucial idea we need to cover, and that's the difference between the perfect world of our equations and the messy, real world we all live in. You see, in theory, we imagine these perfect, reversible processes. things that could be perfectly undone, like running a movie backward. But in reality, every single thing that happens, and I mean everything, is irreversible. You can't unbreak a glass. My coffee is never going to spontaneously get hotter by sucking heat out of the cool air in this room. The flow of time and energy is a one-way street. And with every real process, some of that useful, organized energy gets lost. And that brings us all the way back to our cup of coffee. As it cools down, it's a tiny, tiny echo of a universal trend. If every single process in the cosmos, from a star burning out to our own bodies working, is irreversible and always moving towards a state of more disorder, what does that mean for the ultimate fate of everything? It's a huge question that starts in a warm drink and ends at the edge of cosmology itself. Definitely something to think about with your next coffee.